and welcome to this manufacturing process technology part 2 module 14. We were talking about why it is important to have a parity between the experimental and theoretical derivations of the MRR in case of USM, and we found out that although the theoretical expression that we arrived at has Q or MRR proportional to the 1/4 of the average grain diameter, in reality, in experimental reality, the MRR is actually proportional to the diameter to the power of 1. And we were further discussing how M.C. Shaw wanted to explain in his theory why this proportionality to single power of d comes because of certain assumptions. So, what M.C. Shaw assumes is that the grain actually is not really a spherical shaped grain, but if we look at the grain very closely, the grain is comprised of many big and small surfaces, and basically that is what results in an altogether different projection of the surface of the grain. And although the grain has an average diameter of small d, as had been discussed earlier, the surface of the grain may have an altogether different diameter. So, if I project the surface and try to see what is the diameter of the surface, it may have an altogether different diameter, and this diameter d1 can be assigned to the surface projection of a grain. So, although when we calculate the number of grains making impact all at once between the tool and the workpiece, and in calculation of Z we may consider the average grain diameter d, but actually while calculating the flow stress, it is not that average diameter d which participates, but the projection diameter d1 which actually participates. Okay. So, in a way it is the surface which is responsible for the indentation. And the concerned diameter that we should take should be d1 and not d, okay, as far as the flow stress calculation happens. So, in fact, the discrepancy of why q is not proportional to d to the power of 4, but is proportional to the single power of d was explained through this theory as proposed by M.C. Shaw, and he proposed that instead of having a smooth surface, the grain would have projections of average diameter d1. Further, it is observed that if we look at number of values d1 and number of values d, the d1 which is the projection diameter is much smaller in comparison to d. Okay. You have to remember what we are talking about, d is actually in the microns range. So, it could be something like, let us say 25 microns for example, so it is 0.025 millimeters, and squaring that would result in a much smaller diameter. So, typically this projection diameter d is proportional to square of the average grain diameter, or the diameter d1 much smaller value would be equal to mu times of d square, but d is the average diameter of the grain. So, that is how we had to plug in whenever we want to calculate the flow stress sigma w, which was calculated earlier in case of USM. So, let us now go back to the material removal rate equation, which talks about Q to be proportional to, in this case it has to be d1 h w to the power of 3 by 2, obviously because the d gets replaced by d1 here, which is actually the projection which participates or interferes with the surface in order to produce the material removal, times of z times of new frequency of the tool head, and h w square comes out to be equal to 8 times of the average force times amplitude A divided by pi z d1 h w times 1 plus lambda. Z still remains equal to rho c by d square, because you have to think of it that even if the projection diameter of the grain is different, the number of grains making impact would still be related to the average grain diameter d. So, if this diameter is lower, the z would increase and vice versa. In other words, instead of the fact that there is a projection diameter much smaller with respect to the d, and so d plus d1 can be approximated with d, the value of z, or the number of grains making impact per cycle, always is inversely proportional to the square of the diameter, okay, as before. So, we put all these values, plug all these values and try to find out what is effectively the result of all this. So, Q therefore becomes equal to, again if I just wanted to substitute h w back into this equation, we have d1 times of 8 force average A divided by pi z d1 h w 1 plus lambda to the power of half whole to the power of 3 by 2 times of xi c by d square times of nu. In other words, Q, if I solve this algebraically, becomes directly proportional to power of d to the power 1, f average to the power 3 by 4, amplitude to the power 3 by 4, concentration of the grains to the power of 1 by 4 times of frequency of the tool nu divided by h w to the power of 3 by 4 1 plus lambda to the power of 3 by 4. So, as you can see here, the Q actually becomes equal to the first power, or directly proportional to the first power of d, which is what we started with, which was a disparity between the earlier theoretical model and the experimental observations. So, Q therefore becomes proportional to d to the power of 1. However, the Shaw theory has some limitations. Let me just point that out step by step. It does not correctly predict the effects of variations of amplitude, average force or frequency. So, obviously, if f would increase, the MRR should also increase, because as I earlier illustrated in the last relationship, Q is proportional to the force to the power of 3 by 4. However, if we actually start looking experimentally, force plot experimentally, it is illustrated here that corresponding to some particular feed force, there is still a proportionality maintained between q and f to the power of 3 by 4, beyond which there is a complete deviation in this region from the theoretical. And this effect is more because there is something called grain crushing, which you can't avoid. Supposing there is a certain stress value, certain average force value of this tool, and obviously force per unit area, which does all this brittle fracture on the workpiece. So, there may be a critical force, a cutoff force beyond which the stress applied to the grain would result in the grain getting crushed or getting fragmented into pieces. And so, because of that, you may not have a grain available anymore for doing the material removal, because all the grains seem to be crushed at that particular high frequency. So, in that event obviously the MRR has to come down. So, the actual MRR comes down because of such an effect, where these effects may not be able to get really predicted by the Shaw theory. Okay. So, there are many other associated factors which has to be clubbed to the material removal model, which has been suggested earlier by Shaw theory, so that it can really fit well the practical situation. The other thing that would like to say is about how there is a change of the MRR with respect to the various parameters like frequency, amplitude, feed force, hardness ratio of the tool and the workpiece, that is lambda, the grain size, concentration of the abrasive in the slurry, so on and so forth. So, let us for example look at frequency. So, obviously the material removal rate varies linearly with respect to frequency, and so theoretically it should be a straight line plot as seen by the dotted line here, but in the actual case, if you remember, the way we predicted the frequency was on the basis of, or the velocity of the tool was on the basis of an average made between the amplitude and exactly 1/4 of the time period. So, that is actually not a very good estimate of the velocity of the tool, which would lead to obviously errors in the frequency. So, actually the frequency and material removal rate are related to each other in a not so linear manner. You can see this is how the actual material removal rate varies with frequency. Similarly, for variation with respect to amplitude, obviously there will be a increase in the MRR if the amplitude also increases, but as you vary the frequency and the combination of amplitude and frequency, you will see MRR to be more and more as the amplitude varies along with the frequency. So, this is for example a higher frequency, and nu 3 is the lower frequency, and you can see that with respect to the amplitude on a certain frequency, you have more or less direct proportionality between as estimated by the Shaw theory. Similarly, we can look into how the material removal varies with respect to the feed force. So, obviously as the amplitude increases, the material removal rate should also increase, because you will have to again remember the same formulation Q proportional to d to the power of 1, f to the power of 3 by 4, amplitude to the power of 3 by 4, concentration 1 by 4 times of nu the frequency divided by h w to the power of 3 by 4, 1 plus lambda to the power of 3 by 4. So, here as we can see that with increasing amplitude and with the increasing feed force, there is a tendency of this material removal rate Q to go up. So, as the amplitude increases, let us say this is A1, A2, A3, different amplitudes where A1 is more than A2 is more than A3. So, obviously at a lower amplitude the material removal rate would be lower with respect to feed force in comparison to what would happen at a higher amplitude. So, it is also notable that the grain crushing effect leading to a reduction in the material removal is probably corresponding to a lower amplitude. The grains can withstand lower force in order to get crushed in comparison to a higher amplitude. You can think of a relaxation effect here, that If the amplitude is more, then the grains would have more time between two impacts of the hammer, and therefore they can last longer. So therefore, if the amplitude is more, it has that time relaxation effect, because of which the average force at which the grain crushing would happen would shift between these 3 points A, B and C. So you can see at the highest amplitude the grain crushing force is shifted towards the right, or is the maximum the grains can take. Similarly, if I had to compare, or if I were to compare the lambda, which is actually the hardness ratio between the work and the tool, with increasing lambda, material removal would obviously decrease, because as q is proportional to, inversely proportional to 1 plus lambda to the power of 3 by 4. So that is how we can have an estimate of what would happen to material removal with respect to lambda. Okay. So for certain materials like glass, brass, tungsten, titanium, steel and chrome, you can see that the more brittle the material is, the better the removal rate is. For example, in all these materials, glass is the most brittle material, and you can see almost 100% material removal rate in comparison to some of the more ductile ones like brass, tungsten, titanium, steel, where the percentage of material removal is much less in comparison to that of the brittle material. So you have 6.6 as opposed to 100, which is quite an increase. So all the process when it was designed to begin with was really for the brittle materials, but later on because of the utilization that it had, it is a passive process, people used it for a variety of even metal removal applications as well, but at the behest of getting a very low material removal rate. So let us look at how the same Q would vary, or material removal rate would vary with respect to the diameter. Again, the same problem here, that at a certain critical diameter the grain crushing effect would start to take place if the diameter is higher, and so the material removal rate obviously would be lesser in that instance. And so with the concentration, so corresponding to a certain critical concentration, the material removal rate peaks, beyond which it plateaus, because you can think of it that even if the concentration is increased any further, the Z value is more or less limited, So it is occupied at a certain loading, almost full space between itself and the workpiece with abrasive grains. So even if you vary the loading beyond that, what is going to be the effect? There is no extra grain that is going to come in, because the area is already occupied. So therefore, you have a criticality of concentration beyond which increase in concentration may not result in any further increase in the material removal rate. Similarly, with viscosity, if I were to look at how material removal gets changed, so higher is the slurry viscosity, lower would be the material removal, obviously, because the way that the fragments get carried away is through the process of diffusion, and diffusion is more interstream, and so if the shear between the layers is higher, then the diffusional effects may be lower, and therefore there may not be a tendency of the broken pieces to go as frequently as would happen if the diffusion, if the viscosity was lower. Okay, so those are some of the process parameter details. Let us also look at the dependence of surface finish on the grain size. So if the grain size is more, obviously the average roughness would increase, and it would increase more in case of a brittle material than in case of a hard or a ductile material. And so the effect becomes more prominent of the mean grain diameter increase on the average surface roughness if we were talking about a brittle material rather than a ductile material. So let us now look at some instances of numerical problems and try to see how we can find out the material removal rate, or how we can determine the percentage in the change in the machining time for a USM operation. So in this particular problem, we want to determine the percentage change in the machining time related to an USM process while cutting these tungsten carbide plates when the tool material is suddenly changed from copper to stainless steel. So obviously the hardness of copper would be different in comparison to that of SS. So the HT is going to change from copper to HSS, and that is going to be changing the material removal rate. So we already know that if let us say QS and QC are the MRRs with copper and the stainless steel. So, QC by QS can be represented as 1 plus lambda s divided by 1 plus lambda c whole to the power of 3 by 4. This is borrowed from the MRR equation as theoretically obtained earlier, and lambda c happens to be the hardness of the workpiece, which is tungsten carbide, by the hardness of copper. Similarly, lambda s happens to be the hardness of the workpiece by hardness of SS or stainless steel. So, the if we look at WC, it is much harder. Okay. So, the hardness of WC is much harder in comparison to either copper, okay, or stainless steel. And so, this ratio really, what is lambda c or lambda s, is much greater in comparison to 1. Okay. And I can actually replace this by just a ratio lambda c by lambda c, neglecting lambda s by lambda c, neglecting the 1 term. It is much greater in comparison to 1 to the power 3 by 4. So, this becomes effectively equal to the hardness of copper by hardness of stainless steel to the power 3 by 4, and we already know that from common literature that hardness of copper to hardness of stainless steel is actually 1/3. Stainless steel is about 3 times harder than copper. So, we can get the QC by QS to be equal to 1/3 to the power of 3 by 4, which is 0.44. In other words, the time scales, if we look at from the copper tool and the SS tool, which is actually equal to, or which is inversely proportional to the material removal rates of the stainless steel in comparison to copper, becomes equal to 1 divided by 0.44, that is about 2.27 times. So, the time of a copper tool or is at least 2.27 times more than what is obtained on a stainless steel tool. So, in other words, if I want to see what is the percentage reduction when the tool is changed from copper to stainless steel, it can be represented as T copper minus T stainless steel by T copper and 100. So, that becomes equal to 1 minus 0.44 or about 56%. So, there is a change of time of almost the order of 56% when we are changing the tool material from copper to stainless steel, talking about the USM process on a tungsten carbide plate. So, similar numericals can be derived when even the workpiece material gets changed, and a ballpark figure could be arrived at about what is going to be the difference in the timing of machining based on change of the tool as well as the workpiece materials. So, we will actually look into a material removal numerical problem, but in the interest of time I will close this particular module, and in the next module we will start looking at how numerically we can estimate the material removal rate in a situation, and that would help us to also estimate the machining time for a certain geometry that has to be cut within a certain work material. So, with this I would like to bring to an end this particular module. Thank you very much.